So I come from the what's called the performance engineering team in Red Hat, and so I'm not a developer necessarily for Open vSwitch, but I focus more on the characterization side. And for the past couple of years, we've had a lot of work on DPDK acceleration, in particular in OVS, and tailoring mostly towards like the telco sort of use case. Now, let me make sure I can figure this out. Okay, good. So why does the cache matter? In the per-PMD, you basically follow the sequence of events. You're receiving packets, you identify a packet, you look up an action, and you execute an action. And in each PMD thread, this is serialized, and so looking up what to do is important to your performance. The EMC, I don't do a good job of defining it here on the page, but it's the first and ideally the fastest cache to find out what you need to do for acting on this packet. In order to test this, we use a relatively recent, it's a couple generation old, Intel server, 2-socket, Haswell, as it's known, with two 25 gigabit controllers. And we use a traffic generator that's also DPDK based to generate the packets and measure what packet loss we have. Just a couple notes on the testing methodology itself. We do obviously use Open vSwitch. We're using the DPDK latest branch from 25th October is when we started these tests. We build with a couple optimizations, and we're using DPDK 18.11. We have 2 cores dedicated for OVS on the same NUMA node, and when we configure OVS, we're not doing anything like Mac learning. We're just doing simple port forwarding rules here. We're trying to focus on strictly the performance of the cache lookup and not any other aspects. For Linux, RHEL 7.5, we do use a CPU partitioning profile, which comes from a TuneD package with RHEL, which just makes it very convenient to do CPU isolation. So if you want to isolate CPUs for something like OVS or something else, and you want to make sure you're absolutely certain that you have the minimal amount of preemption from kernel or anything else, this CPU partitioning profile will give that to you. The benchmark is RFC 2544-like. It's software-based, and we measure maximum throughput while not exceeding a certain % loss. In our benchmark, we have something called binary search, so we break out the binary search logic from the actual traffic generator action, and that way we can plug different traffic generators. And at the moment, we support T-Rex and MoonGen. So the binary search logic does support multiple device pairs. We can scale to hundreds of millions of packets per second and several adapters in a single test. So we pretty much can cover most use cases or most devices under test. We also have, as part of pbench traffic gen, the ability to start a number of tools. This could be perf, trace command. We also have one for Open vSwitch, which collects basically all the Open vSwitch statistics that are provided either from PMD stats or some of the other Open vSwitch information. Again, the binary search, we conduct a trial at a specific a transmit packet rate, and of course we adjust the trials based on whether we pass and fail. We do have a couple optimizations here, especially for zero loss, where we want to test for a long period of time. We can have trials with different trial time periods, and as we progress in the test, we'll use longer and longer trial periods until we get to our final validation trial period time, which just saves us some time for some of these tests. The pluggable traffic generators, the one we're using for this is the second one listed here, the T-Rex TXRX profile.py. This allows us to define a number of traffic streams. As we'll see here, we can define one or more traffic streams, the characteristics like the flow, what are you using to modify the flow, the length, the frame size, and also some things here like towards the bottom, if you see stream types, teaching warm-up. That allows us to send packets out that are strictly not for measurement, but allow for your switch infrastructure and for OVS to learn the path or learn flows before actual critical measurement's done. So EMC. EMC should be the fastest way to process packets, and I'd say in many cases it is. The graph here is comparing EMC to just no EMC at all, just Megaflow or a data path classifier, and with the 225 gig networks. And as you can see here, it's almost 25 million packets per second. It's extremely fast, and it's most people who probably just cursorily measure this comparison would find that it's faster. This one was done at 100 flows. But as we move to 30,000 flows, EMC is actually slower than not using EMC. And this is the problem that we encountered. We actually saw this with customers, and they asked if we should be disabling EMC, and we wanted to answer this question. So here's the Megaflow performance stayed the same, roughly, and yet EMC went from 25 million down to about 15 million. So it's quite a big drop. So what explains this drop? This is the same type of test, but plotted over several different flow counts from the traffic generator, anywhere from 100 to 30,000. And the yellow line plots the EMC hits per second, and you can compare that to the red line, which is the performance while using EMC here, the peak performance. As you can see all the way towards the left, where we're at 100 flows, the number of hits is roughly equal to the number of packets you're processing. You're getting 100% hit rate. But as we move to the right, the number of hits drops very significantly, very quickly. The EMC is, in theory, able to cache around 8,000 flows, but we fall way, way below that as we increase flow count. You can see it between, let's say, 100 flows and 1,000 flows, we drop very, very significantly, and we start to tail off eventually. So unfortunately, we're just not getting the benefit of EMC here. So what could we run instead? We could add SMC here. This is the signature match cache. It's able to cache or contain a significantly higher number of flows, but it doesn't have quite the raw performance of EMC at the low flow count, but adding it with EMC does at least improve the overall performance. If you look at the red line here, it doesn't drop as much. The gap isn't as large compared to running just Megaflow. So we're comparing EMC with SMC in red versus no EMC and no SMC in blue. We also plot the EMC hits per second. You can still see the same significant drop of EMC hits as we increase the number of flows, but and to make up for this, now we have the SMC caching those flows. But again, we still have lower than just Megaflow caching here, greater than, say, 3,000 flows. So it's not providing across-the-board performance improvement for us. If we go to SMC-only flows, so we're actually disabling EMC, now we finally have better performance than just Megaflow. So the red line here, SMC, Megaflow, MPPS, that represents, with SMC enabled, we're just under 20 million packets per second for just about any number of flows, roughly 3 million packets per second more than just Megaflow. The SMC hits per second is also exactly in line. Incidentally, when we were collecting these stats, the SMC hits are always slightly higher than the number of received packets, which really doesn't make much sense, but that's just what was reported, but you can probably treat these as roughly equal. We do have one issue here. This is comparing SMC, only SMC to only EMC, and that's at the really low flow count. We still have a very significant gain for EMC at that small data point. And that's what we would really like to be able to remedy here. For SMC performance, we see these two functions stand out here. They're the DPCS rule matches key. We'd like to see if there's a way we can optimize these and see if we can improve that, and hopefully solve the case where at the low flow counts where EMC is outperforming. Summary, I think the EMC it is performing pretty well when it's at 100% hit rate. I think it has the potential to do extremely well. We just have to figure out why we're not getting the hit rate we expect. Anywhere above a couple hundred flows, we're seeing very, very low hit rates. So we don't know if this is collisions for the hash calculations for different flows, so we're just not getting the effectiveness of all entries here because of that hash calculation or something else. The other possibility is that when we know the flows are significantly higher than the EMC, could we automatically actually disable EMC at runtime? I mean, we know we can disable it at runtime today, but can we do it automatically? Could we detect that if you have a scenario where you have thousands or maybe millions of flows going through OVS, it really doesn't matter how fast you make EMC. If it has a small cache size, it's not going to be effective. So if we could just monitor, use heuristics to identify the situation where we have a very high number of flows, we could just disable EMC temporarily. And if we reach another situation where we return to a low number of flows, we could enable it. The SMC, in particular without the EMC, does perform best in almost all these flow counts, only under 200. However, the SMC, using it is greater. We would like to see if we can optimize this. One option maybe going forward is that could we just consider using the SMC and not EMC by default? If we think that applies to a more general use case or most users, would it be better just to flip them? Because right now I believe SMC is off by default, but EMC is on. And that's all I have for presentation, and the rest would just be questions or discussion.
Let's thank our speaker. And we have plenty of time for questions, so go ahead, Ian.
So it was a really good talk, by the way. I would think just on the SMC, possibly one of the roadblockers there is that it's still considered experimental. But that's maybe something for us to discuss as well. What is experimental and how do we get things out of experimental? We've kind of left a few features in the past there for a while, but a few suggestions on that we're happy to work. And I think there's definitely some optimization work on the SMC side that could be done. So I think if you guys have any input there for the Intel labs, I'd be happy to help out on that side as well.
Yeah, we'd be happy to provide some more performance testing or just more use cases, like if you wanted us to test to a much, much higher number of flows or just different situations for SMC, I'd be happy to do that. And yeah, if we can just get past the experimental stage and it makes sense, then that would be great.
Yeah. No, and it's just encouraging to see that it's being used and it does make a difference. So I think that's half the reason the experimental tag gets put on it first. Make sure A, it's not broken, and B, it's of use, and it seems it is. So thanks.
Okay.
Yeah, in your test, your default cache size is 8K?
The cache size for EMC,
for EMC, yeah.
It's 8192, so it's relatively small. The SMC, I don't know the exact size, but it's referred to as being able to handle millions. But I don't know if there's, at least from the documentation, it said possibly 1 million flows. I have not tested that yet, but it would be easy for us to actually test that, go to 1 million flows and monitor the SMC hits per second and compare it to the receiving packets and figure that out. The SMC, I believe, I'm certainly not intimately familiar with SMC, but it's designed to be significantly more data efficient, and therefore it can cache a very high number of flows. Well, I'm sure we have some people from Intel who can go over it in more detail.
Yeah, I know Ipan Wang did SMC. He said if we have many flows, SMC is better. But I think we can choose default cache size for EMC, right? We can use a bigger number than 8K. Maybe it's better.
Possibly. We actually tried that, but we didn't see much of a difference. So we think there's something else wrong with either computing that hash and having hash collisions, and we're just not getting the effectiveness of the EMC size, practically no matter what it is. Because if we look at a couple of the graphs here, this one or this one, you see in the yellow here, the EMC hits per second as compared to the number of received packets per second. It goes down quite significantly, and even at like 5,000 flows, we're at probably 2/3 of the receiving packets are getting an EMC hit. Whereas the EMC being 8,000, we should be able to cover that easily. So I think we need to address why we're not getting the hit ratio that we should be, even when the number of flows is fewer than the capacity of the EMC. Once we figure that out, then we could work on perhaps increasing the size of the EMC.
Okay, thank you.
Actually, on that point, we've tested, when you say 100 flows, there's 10 different ways of creating 100 flows. So that top list algorithm in that particular NIC you've tested behaves in a certain way when you modify certain places in the packet versus others. So we've seen certain 100 flows where you get up to 100% match when you go to up to 8K, and certain different ways you get 100 flows, you start colliding earlier. So it really depends on what you're sending it to.
And I should probably state, the way we're creating different flows is we're incrementing both source and destination MAC
and what also
IP.
matters is that when you use software traffic generators, those tend to send bursts. That 32 or 64 packets get out as the same flow sometimes. That makes things faster as opposed to hardware generators that would actually sweep through it within the burst. So those also make differences.
Yeah, I believe we are sending a different flow for each single packet in our case, but I certainly believe that could be the case for some. But perhaps just the way we're constructing our flows is not conducive to getting that nice hash match in the EMC. We could probably devise something that maybe is more random and just see if we get a better distribution and a better hit ratio.
Are there any more questions? All right, let's thank our speaker one more time.
Thank you.